Now that we have reviewed how to draw Lewis structures of molecules, we're going to take a moment in this video to discuss resonance forms. So oftentimes, more than one Lewis structure is possible for a particular molecule. Um, and when this occurs, it's described, the true structure of the molecule is described as a combination of all reasonable Lewis structures called resonance forms, right? So again, the key is reasonable Lewis structures, which can be very difficult at times for some students to even understand the concept of reasonable Lewis structures. But again, following the rules that we've established, this is what we're talking about, right? And these resonance forms are simply different electronic representations of a particular molecule, right? So notice um, only electrons and the placement of electrons is different between two resonance forms. So a very important concept to understand is that only electrons can move, not atoms. And this is going to be a very basic theme throughout organic chemistry. We're going to discover that reactivity occurs when electrons move from one atom to another atom, or from one bond to another, right? Let's take an example of HCO3 minus. So HCO3 minus, hopefully from general chemistry, again, nice little review, is the bicarbonate ion. And if we draw the Lewis structure of bicarbonate, the hydrogen is attached to one of the oxygens, so carbon is a central atom. The three oxygens are bound to carbon, and the hydrogen is bonded to one of the oxygens. And we get a structure that looks like this, right? Now, in terms of placement of electrons, we know that the oxygen in the left bottom there has two pair of electrons. We also know that the oxygen at the top has two pair of electrons, and the oxygen on the bottom right has three pair of electrons. And I'm going to draw the third pair in red because what we have is we have a negative charge on this particular structure. The hydrogen has zero formal charge. The oxygen connected to the hydrogen has zero formal charge. The carbon has zero formal charge. And the top oxygen has zero formal charge. And so the formal charge of the oxygen on the right has a negative formal charge. Now, oftentimes that formal charge tells us something about that particular atom, and when it's negative, it means that that atom is electron rich, and when it's positive, it's electron deficient. This comes in handy later on, so it's something I'm putting these little nuggets into your mind for future references. But we can draw a resonance structure in which that red pair, now it's arbitrary, I could have picked any of the three pair of electrons, but that red pair is going to form a new bond between carbon and oxygen. Now notice I'm drawing the arrow from the electrons, from that pair of electrons, the red pair of electrons, to the bond because I know that it's going to form a new bond between carbon and oxygen. Now when it does that, I have to remember I can't violate any rules, especially the octet rule. So if I'm adding a pair of electrons, that means carbon is going to have a new bond to it, which means it has 5 bonds or 10 electrons around it, and that can't happen. So what needs to happen? I need to break another bond, and so I can take a carbon-oxygen pi bond, and I can move that pair of electrons up to the oxygen, right? And so I draw a resonance structure. Now notice my arrow. My arrow has two heads, right, on that line. And this is what's called a resonance arrow. You're going to see that the arrows that we use are very particular in terms of what we're trying to demonstrate. If we're demonstrating resonance, we see this arrow. If we are demonstrating equilibrium, we see a different type of arrow, which I'll show a little bit later on. So now when I'm drawing the new structure, I have a connectivity that's a little bit different. Notice the carbon-oxygen double bond initially. Now one of those bonds is broken, and the oxygen has now 3 pair of electrons around it, and it has a negative charge. And now the original carbon-oxygen single bond has a double bond on it, and the oxygen only has 2 non-bonding pair of electrons around it, right? And so these are 2 resonance forms. They are actually equivalent forms, which means that those pair of electrons actually oscillate between each of the oxygen atoms, right? So a true representation of the bicarbonate anion is actually a blend of these 2 structures. So understand, Lewis structures aren't always perfect, right? And resonance forms try to give us a little bit better picture of what the true structure of the bicarbonate or of any particular structure really is. So let's think about curved arrows and how we use them. Understand that curved arrows always run from the pair of electrons, right? So they never run from an atom, they're always coming from a pair of electrons. And they're always going to an atom or a bond. So from a pair of electrons, which is a lone pair of electrons or a bond, to an atom or another bond, right? Also, there's formalism in the arrow itself. So this type of arrow, an arrow that has a double barb, it's called, denotes the movement of 2 electrons. So we can think of each side of the head as representing an electron. So a double barbed denotes the movement of 2 electrons, and a single barb denotes the movement of 1 electron. Oftentimes this single barbed arrow resembles that of a fishhook, and so you'll see that referenced as a fishhook arrow. So when we're moving 1 electron, we use a fishhook arrow, and when we're removing 2 electrons, we use a double barbed arrow. Let's look at a couple of examples. Here I have a structure in which it kind of looks like ethylene, which was in a previous video, except that a pair of electrons are on 1 carbon and the other carbon doesn't have a pair of electrons. And the carbon that has a pair of electrons has a negative charge. The carbon that doesn't have that pair of electrons has a positive charge. And of course, this isn't going to be very stable. 1, because the carbon on the right doesn't have an octet of electrons. 2, because we have a separation of charge. So what can we do? Well, we can donate that pair of electrons into form a new bond between the 2 carbons. So notice where my arrow is going. It's going from the pair of electrons to the bond. And I can draw a new structure, and that structure shows that new bond forming. And when I look at the formal charges, each carbon now has a zero formal charge, and this is the better resonance form of ethylene, right? So these are 2, understand, these are 2 resonance forms of ethylene. The one on the left is a minor resonance form. The one on the right is the major resonance forms, and we'll talk about how to distinguish that in just a little bit. Another example is this is the allylic carbocation. I'm going to explore the allylic carbocation in a little bit more detail later on, but here you have a carbon that has a positive charge on the right. It's electron deficient, and so I can simply draw another resonance form of this particular structure by taking a pair of pi electrons and simply moving them, right? Because remember, bonds are electrons. Now, you're also going to notice that this happens a lot when you have pi electrons. So when you have a double bond or a triple bond, a pi electrons can move easier than sigma bonds. If I move a sigma bond, that means I'm breaking the bond, the entire bond between two atoms. That requires much more energy than breaking one bond but still having a bond between the two carbons. So I can move a bond, a pair of electrons still, so I'm using that double barbed arrow, and the result is that I now have a bond between the carbon, the central carbon, and the carbon on the right, and now I only have one bond between the central carbon and the carbon on the left, and it now has a positive charge. So one of the things that you are going to notice in your practicing is that we always maintain any charge. Notice the example on the top there. The carbon on the left has a negative, the carbon on the right has a positive charge. Overall, though, it has no net charge. The resulting structure of ethylene also has no net charge. When we look at the allylic carbocation, it has a net positive charge, and so both structures show that net positive charge. And again, both of these are resonance forms of the allylic carbocation. Now, here's another example in which we're actually going to be breaking a sigma bond, and I'll show you the difference between breaking a pi bond and breaking a sigma bond. All right, so here I have the carbon on the left has a negative charge. Now, of course, this is not going to be very stable, right? Because carbon tends to not like to have charges, and we're going to explore the reason for that later on. But if we donate a pair of electrons, like we've done in the past, to create a new bond, a pi bond, we run into a problem. The problem is that the carbon on the right already has 8 valence electrons, or 8 electrons around it, excuse me. So it satisfies the octet rule. Placing another pair of electrons violates that octet rule, so we have to break another bond. If X represents some group that can leave, then I can break that bond in which the pair of electrons from that bond moves toward the X, right? Now this is not, understand, this is not a resonance form. This is an equilibrium. This is an actual reaction that takes place, right? So when we talk about reactions, we're talking about equilibrium processes, and so we use an equilibrium arrow. Notice the difference between a resonance arrow and an equilibrium arrow. The result is I've now formed my pi bond between the two carbons, which if you look closely enough, you'll notice this is ethylene. Also resulting from this is that X has taken a pair of electrons. If X is neutral and it has accepted that pair of electrons, then it automatically has to take on a negative charge, right? And so again, think about the balancing of charges. We start off with a molecule that has a negative charge. We end up with two molecules, one that's neutral, but the other has to have that negative charge. Another example is something like this, right? So here I have this chain of carbons. There's single bonds and double bonds, and it's alternating between a single and double and single and double and single bonds. And if you notice closely, I'm missing something. The carbon on each end has only 6 electrons around it. Well, I'm going to add an electron to each carbon. When I do that, the carbons don't have an octet of electrons around them, but they are neutral. So they're neutral species. Whenever you have an unpaired electron that is neutral, it's called a radical. So when I have two unpaired electrons, this is called a diradical. Now, I can draw a resonance structure of this diradical. But I'm only going to be moving one electron at a time. And so I want you to follow along in how I do this. So I'm going to start on the left side, and I can donate that one electron to form a bond between the two carbons. But a bond consists of two electrons, and I only have one. What can I do? Well, I can take one electron from one of my pi bonds. That's going to leave me with another electron that's left. Well, I'm going to take that other electron and I'm going to move it over to form a new bond between carbon 3 and carbon 4. Again, that's only one electron, so I'm going to take an electron from the double bond of carbon 5 and 6, which leaves me with a lone electron, which I can then take to form a bond with my last electron. This is how we denote the movement of one electron. The result, again, it's a resonance structure where now I have a double bond between carbon 1 and 2, a single bond between 2 and 3, a double bond between 3 and 4, a single bond between 4 and 5, and a double bond between 5 and 6. Now, one thing that I slightly mentioned earlier is that all of these examples, except for the bicarbonate, are what we call weighted averages. And what that means is that one of the resonance forms contributes more than the other. The question then becomes, how do you determine the actual weight of the resonance, of each resonance form? Well, I'm going to give you some guidelines. And first and foremost, and one of the things that is always good practice is to think about whether or not each atom in a particular Lewis structure has an octet of electrons, especially when we're dealing with the second row elements, which is our main focus in organic chemistry, right? So the second row elements almost always have to have, or they're striving to get 8 electrons. And when you have that, that's typically your major resonance contributor, right? But in general, I'm going to give you some rules. And the first rule is simply this: the more bonds in a structure, the greater the contribution. The more bonds in a structure, the greater the contribution. Let's look at an example of this. So here, this is a protonated version of acetone. It's a ketone, which we'll get into functional groups in the next chapter. But the oxygen, notice, has a formal charge of a +1. So oxygen, again, formal charge tells us that there's electron deficiency. And oxygen's really seeking more electrons. Well, how does it gain more electrons? I can draw a resonance structure of this structure in which I take a pair of pi electrons, so that double bond again. So I'm going to take one of those electrons. Notice I'm not breaking a bond. I'm not breaking the bond between carbon and oxygen. I'm simply breaking a pi bond between carbon and oxygen. So there's still a bond between the two, which I can do in terms of drawing resonance structures. And I'm going to move those electrons to the atom itself, right? The result is now I only have a single bond between oxygen and carbon, and the oxygen now has two pair of electrons around it, which means that it has no formal charge, right? It has 8 valence electrons minus the 4 non-bonding electrons minus the 2 bonds. So, I'm sorry, 6 valence electrons, I said 8. 6 valence electrons minus 4 non-bonding electrons minus 2 bonds gives me a formal charge of 0. And of course, carbon also still has bonds attached to the two carbons that, so we didn't break any bonds there. But notice now carbon only has 6 electrons around it, right? So number one, it doesn't satisfy the octet rule. So that should give you a clue as to which one has the greater contribution. But number two, it has the positive charge. So again, we start off with a structure that has a positive, net positive charge. We end up with a structure that has a net positive charge. All right, which one of these has the greater contribution? Well, notice in the structure on the left, we have a total of 1, 2, 3, 4, 5 bonds. And the structure on the right, we have a total of 1, 2, 3, 4 bonds. So, because the structure on the left has more bonds, it has the greater contribution. And sometimes you'll see that it's called the major resonance contributor. The major resonance contributor, right? That's the first rule. First and foremost rule. The second rule is that separation of charge is bad, right? If I can have a Lewis structure in which the formal charges of all the atoms is minimized, that's going to be the major resonance contributor. As an example, again, we're going to use that carbon-oxygen double bond because in general, with double bonds, I can move one of those bonds. This is formaldehyde. So carbon has a single bond to each hydrogen and a double bond to a carbon. Now, I can again move electrons from that carbon-oxygen bond to oxygen. Now, you might be saying, well, why oxygen? Why not carbon? The reason for this, again, deals with that reasonable Lewis structure drawing, right? Between carbon and oxygen, oxygen is more electronegative. So if there is a bond between two atoms, and electrons are going to flow to one of them, they're always going to flow to the more electronegative element, and not to the more electropositive element. So even though you technically could take the pair of electrons and move them to carbon, that is going to be an extremely minor, and it's not what we consider a reasonable Lewis structure, right? But drawing, moving the pair of bonding electrons to the oxygen, we can get a resonance structure in which now the carbon oxygen bond is only a single bond. The pair of electrons have moved up to oxygen, so now instead of having 2 pair of electrons, it has 3 pair of electrons. Notice it also has a formal charge, right? Oxygen has 6 valence electrons, 6 minus the 6 non-bonding electrons minus the 1 bond is a -1 charge. And so this is important to denote as well, right? we have a plus on the carbon, just like above, because carbon only has 6 electrons around it, and we have a minus on the oxygen. Again, just to review formal charge, carbon is plus 1 because it has 4 valence electrons minus the 3 bonds. That is a plus 1, right? So here we have 2 resonance structures. The one on the left has 0 formal charge on all the atoms. The one on the right has a negative charge on the oxygen and a positive charge on the carbon. So even though these two are resonance contributors of formaldehyde, and I want to make that clear to you, both of them are contributions to the structure of formaldehyde. And as a matter of fact, we're going to see sometimes it's easier in terms of chemistry to visualize the Lewis structure on the right than it is the Lewis structure on the left, because it plays a role in the true structure of formaldehyde. That being said, the structure on the left still is the greater contributor because, number one, it has more bonds. Number two, it has minimized formal charges. Okay. The third rule is when we're talking about ions, delocalization of electrons is very important. So I'm going to go back to the example that I showed previously, and that is the allylic carbocation or the allele carbocation. So we showed that there is a resonance structure of the allele carbocation in which I can donate that pair of pi electrons to in between the carbon, the central carbon and the carbon on the right that has a positive charge. And my resulting resonance structure looks like this. Now, in this particular case, I mentioned these are actually equal in their resonance forms. I said there's no difference between the two. Why? Because on the left-hand side you have a carbon that has a plus charge, and on the right side you also have a carbon that has a plus charge, and they really look very similar to one another, just like in the bicarbonate anion. Now, when you have this, you can actually draw a better representation that simply shows that there's electrons, 2 electrons, that are actually going in between those 2 bonds, and there is a positive charge, and that positive charge we know resides on both of the carbons equally. Now this is important because, and this is why delocalization is important. Generally speaking, atoms don't like to have charge. When they are ions, something has to have a charge. When you can delocalize the charge between 2 carbons, that stabilizes the particular ion. And so the allele carbocation is stabilized because each carbon is accepting half of that positive charge. Now, the fourth rule has to do with electronegativity. And electronegativity is important in determining, between 2 resonance structures. So here is a structure of what's called the enolate ion. Notice oxygen has 1 bond to carbon. It has 3 pair of electrons, so 6 non-bonding electrons. It has a negative charge. And then the central carbon is double bonded to a CH2, right? So the carbon has 2 hydrogens coming off of it, and then a double bond to that central carbon. Again, we can draw a resonance structure in which we donate a pair of electrons from oxygen to create, right? So I'm going to take these 2 pair of electrons, which is arbitrary. I'm going to donate them to form a new bond between carbon and oxygen. Again, keep in mind that when I do that, that carbon has 8 electrons around it, so I'm adding more electrons, 2 more electrons. I have to break a bond, so I can break that carbon-carbon double bond, and I can move a pair of electrons from that double bond onto the carbon on the left. And so the resulting structure has the carbon having that pair of electrons, and it now has a negative charge, and we have a carbon-oxygen double bond, and now the oxygen is neutral. So the structure on the left, oxygen has a negative charge. The structure on the right, carbon has a negative charge. Again, notice we're only moving electrons around here, and also notice the charges of the structures are maintained. Now, of the two, which is the greater resonance contributor? Hopefully by now you can kind of understand that since we have a negative charge, the atom that is more electronegative can accept that negative charge better than the carbon that is less electronegative. And therefore that would be oxygen. So the resonance structure on the left is the greater resonance contributor. Right? Now, the last rule is this. You cannot violate the octet rule with second row elements. I stressed this at the beginning, but this is one of the biggest mistakes that students make in drawing resonance structures. They think that they can simply move electrons kind of willy-nilly. Well, electrons, in order to move electrons, you have to have an empty orbital to move them. So it's either going to a already empty orbital, or it's moving to an atom in which you're creating an orbital by breaking another bond. So if I take a look at this structure, so this is propene, and I think about all of the examples that we've looked at in this video, and I say, oh, I have a double bond there. Okay, it's connected to a single bond, so I can simply move that pair of electrons to the single bond, right? And so let's say, for argument's sake, that that's exactly what we do, and we try to draw a resonance structure. What's the result? Well, the carbon on the left is going to have a positive charge because I'm taking electrons away from it, so now it only has a bond to the central carbon and then a bond to each of the hydrogens, so there's only 6 electrons around it, so it has positive charge. And now the carbon on the left has a negative charge. I say, oh, okay, well that works, right? Wrong. What's wrong with this picture? Look at it very closely. One of the things that abbreviating structures oftentimes does is students can lose track of how many electrons are around each atom. And if I look at that carbon on the right with the negative charge, it has 3 pair of electrons from the bonds of hydrogen. That's 6 electrons. Plus it has 4 electrons from that double bond. That's 10, so it has a total of 5 bonds, which means it has 10 electrons around it. That violates the octet rule, and therefore this is not a resonance structure of propene.